Okay, everyone. So we are working on the test for the video and audio. So I would like to talk with our speaker, Robin Wei. So can you talk something so we can make sure the video and audio is working? We are
Yeah,
still under
hi
the
Jason. Can you hear me okay?
Yes, very good.
Very well,
Okay,
thank you.
so it seems everything is good. So we can start today's webinar. So we are so glad and honored to have Robin to be our speaker for this webinar. So this is the webinar organized by IDEAS, IDEAS. IDEAS is a nonprofit organization, International Data Engineering and Science Association. We organized a lot of online webinar related to artificial intelligence, big data, data science. Also, we hosted several AI conference at Boston, Dallas, Chicago, Los Angeles. Okay, on October 26 and 27, we will have an AI conference in Los Angeles Convention Center. There will be 3,000 attendees. So that's some background about IDEAS. So I will give the host to Robin, and so we can start today's webinar. Thank you again for all the attendees and Robin, so we can start. Thank you.
Thank you, Jason, and good afternoon to everybody. It's a pleasure to be here. I'm Robin Wei. I'm the president of Corios. We're a data science and data engineering consulting firm based in Portland, Oregon. I started Corios in 2010, and we do our work predominantly with financial services institutions, energy, utilities, and manufacturers. I've been in this line of work for over 30 years. I've built hundreds of predictive models in that time, and I started on the mainframe computer, which many of you might not even have ever had an opportunity to work on one of those things, but it still works with ones and zeros just like everything else. So it's a pleasure to be able to share the topic for today's webinar with you, which is all about measurement and validation of machine learning models in the real world. I've been, as I've mentioned, I've been in this field since the mid-1980s. Some things have changed a lot in that period of time, and many things really have stayed very much the same. The fundamental principles of mathematics and statistics as they play out in analysis of variance and econometrics are still very much the same today, and they underlie a lot of the advances in the field of machine learning and artificial intelligence as we know them today. But the sources of information, the sources of data, the types of data, and the velocity of that information is flying past us at a rate that far surpasses that when I got started in this field. So it's very exciting to see the maturation of our industry and our discipline. But something that has never changed is just how important it is to understand, are we solving the right problem? Have we built a good, is our model a good replica of the way that real world phenomena actually behave? Do we know whether our model is a good one or an average one or a bad one? And how would we know the difference? And how would we know when our model starts to degrade in its performance of replicating and explaining real world phenomena? That is, and finally, how do we make sure that people who are not gifted in the data engineering and data sciences world, how do we make sure that they understand what our models do, that they believe in them, and that they'll use them? And model validation, model measurement is entirely, it's essential to make sure that other people believe and understand in what we're doing, and that they'll use it for better. This is going to be, this presentation is going to start off being somewhat conceptual to describe how did we get to where we are today in terms of model measurement and validation? What are some of the theoretical underpinnings? And then we'll talk about some very concrete, very technical things that my hope is that you'll be able to take this knowledge away and use it in your everyday life. I've also prepared several materials that you can download at the end of this presentation, which should take what you've heard in the webinar today and allow you to expand your knowledge in a very practical way. So stay tuned till the end so that you can get a copy of those materials at the tail end of the webinar. So first, why is measurement and validation so important? The field of machine learning and kind of the conceptual header under which machine learning is a part of that discipline, we now call that artificial intelligence, has taken off like wildfire in the last 3 to 5 years. And the number of people in the discipline has taken off like wildfire. And we have the universities and we have public and private enterprise to thank for their investment of building up the skill of the market of people who practice, who are practitioners in this area. But as we've seen that rapid growth and rapid expansion of the practice of machine learning, there have been some warning signs on the horizon. The first, I think this is a good sort of example of that. This was a topic I saw on Quora. You can see the URL at the bottom here, where somebody asked the question, have you ever seen a data scientist get fired? And if yes, why? And here was a person who provided their own story of why their job was in jeopardy as a data scientist. You know, you usually think that most of the people involved in data science are, you know, there aren't enough jobs, there aren't enough people for all the jobs that are out there. But nonetheless, there are some important realities of some of the risks that we bear in terms of doing our job well. And one of them is to make sure that the people we're doing the data engineering, the data science for, understand how to get the most out of what we do well. And as you can see here in the second highlighted box in this Quora quote, machine learning is seen by many people outside of our discipline as a magic bullet can solve anything. And we all know that's not true, but the rest of the world doesn't understand it. It is important for us to be able to articulate and describe how machine learning works in simple and approachable ways. And I have found in my career that drawing pictures with charts and statistical visualization is one of the best ways to do that. This is not limited to just practitioners. We're also seeing this in terms of corporate stakeholders, like this senior executive from Wells Fargo Bank, who, and this was an article in ZDNet, characterized machine learning and AI as a double-edged sword. And you can see in the quote here is that the regulators who oversee bank and other financial institution activity are asking some serious questions about what are the nature of the algorithms being used that affect customers, such as when you are considering making a loan to a customer, what kind of mathematical model or machine learning or AI model is being used to make that decision. And it's vital that everybody understands it and can measure it, and that everybody believes that it is a valid model for the business purpose. So these are a couple quotes I saw that came out very recently. I think it is absolutely critical to understand we're not actually running into these issues for the first time just now. If there's a famous quote by George Santayana, those who cannot remember the past are condemned to repeat it. The fundamental principles of AI and machine learning are rooted in the financial services world. On the left of this slide, there's a book I strongly, vigorously encourage everybody who's watching this video or this webinar to go ahead and buy it today from wherever you like to buy books, but it's called Against the Gods, The Remarkable Story of Risk by Peter Bernstein. I read this about 5 years ago. It's a fantastic book. It's actually a bestseller, and it walks you through the history of risk and probability, the earliest founders of statistical principles, like the fellow on the right, Jacob Bernoulli. Jacob Bernoulli was a member of a family of very famous mathematicians, his brother Johann, his nephew Daniel. These were some of the most groundbreaking mathematicians of the late 16 and early 1700s. Jacob Bernoulli himself was actually the father of the mathematical constant E, because he studied how interest rates are critical in measuring the rate at which the growth of a financial security grows over time, such as a deposit account or a loan account or what have you. So no slacker in the area of mathematics at all. So Peter Bernstein in the book, Against the Gods, walks you through roughly hundreds of years of the foundation of the field of mathematics, statistics, probability, and risk. And risk today in our modern world is the reason that, that I got really intrigued with the field of machine learning and predictive analytics. I wanted to be able to better explain to my peers and my business partners and my clients how risk can be measured, how it can be modeled, and how we can predict it more effectively. So one field in which mastery of the characterization of risk is fundamental is insurance. So whether this is life insurance or property and casualty insurance or other fields of insurance, actuaries are the mathematicians who specialize in the characterization of risk tied to a person or an asset. And some of the terms that you'll hear as you explore the field of insurance are things like underwriting. Underwriting is the study, it's the part of the field of actuarial science that measures what is the incidence rate of an adverse event, how severe will it be, how will the impact or the pain of that adverse event can it be recovered, and how long will it last? What's the time extent of the pain of that or the financial burden of that adverse event? So they are experts in applying mathematics and statistics, which then give rise to the way that machine learning is used to model actuarial science and the mathematics of loss. Another field in which this is, which risk and the mathematics of risk are at the very basis of this industry, is banking. A different set of terminology, but in particular, one of the key fields in banking, it's not the only field to use machine learning and predictive analytics, but one of the key areas is credit risk. Credit risk is the part of the banking industry, the discipline within banking that models how likely, if we grant a loan to this customer, are they likely to repay it? And some of the things that they measure are, what is the probability of that customer defaulting on that loan if we grant it to them? If they do default on it, how much money is at stake to be lost in that default? That's loss given default. When we multiply the two things together, the probability times the loss given default, we can calculate the expected losses and how much of that default can be recovered. These two industries then use machine learning, predictive analytics, mathematics, and statistics to then, among other things, come up with decision rules around who to grant credit to, how to structure an insurance policy, and how to price it. In both of these industries, the fundamental way that a loan or a insurance policy gets priced is by measuring the risk associated between the customer and the loan, or the customer and the policy, as well as the portfolio of all such loans or all such insurance policies, and the risk appetite of the bank or the insurance carrier. The combination of the mathematical characterization of risk, when combined with pricing, directly derives the profit and loss of that enterprise. So if there was any field in which the use of machine learning was more vital, and if it wasn't these two industries that have been doing this since the 17 and 1800s, I don't know what it would be. So I vigorously encourage you to learn more about how these industries have been using machine learning for a very, very long time, way back before we thought of it as machine learning, back when it was statistics and we were measuring these things with long pieces of paper and a writing instrument and calculating these metrics by hand, if you can imagine that. So we use these characterizations of risk and the way that that plays out in any variety of industries to effectively make decisions. And there is a circular process that feeds on itself that supports this process of decision making. And I want to talk about that and the role that measurement and validation plays in it. It starts with the development of a predictive asset. And that could be a machine learning model. It could be an artificial intelligence model. It could be a neural net. It could be a logistic regression model. It could be virtually anything that assigns a mathematical score to an entity, like a customer or a loan or insurance policy, effectively built by a data scientist in, let's call it the lab, in a quiet and studious environment where they're looking at a bunch of historical information gathered over a long period of time in order to then estimate parameters of a model and be able to render a mathematical score assigned to an entity like a customer or a loan. The next, and while the media, in my view, while the media spends a lot of time focused on the practices of those of us on this webinar who focus on the development of these predictive assets, there's a lot of sex appeal and a lot of intrigue associated with estimating mathematical models. But I'm here to tell you, it by no means stops here. The most important steps are actually yet to come. And the next step is deployment. When we take this mathematical equation and all of the data structuring to build the data on which the model is based, when we take that essentially data structuring logic and mathematical expression of our machine learning algorithm, and we put it into a code base that can be put into production in a computer system that is running every day, every hour, every minute, that's model deployment. Oops. Sorry, something just happened. Hold on just a second. There we go. So that is model deployment. Once we've deployed a model, then we're ready to start as decision makers in a business making decisions using that model around whether to grant a loan to a customer, how to structure the definition of the insurance policy, whether to sell this product to the customer for $5 a unit or for $7 a unit, and so on. Once we start making those decisions in the field, then we want to measure, did we make the right decision? Did we use the analytical results effectively and efficiently? And we measured those things over time. So as just like we deploy the model 24/7, we should be measuring the model 24/7. And once we've gathered enough information over a period of time, that's when we want to validate, is our model a good one? Are we making more effective decisions in the field using this model than if we didn't have it or if we had a different model to use? When we validate the model, then we can decide, should we continue using it? Should we come up with an alternative model? And should we continue to use that asset in the field going forward? Now, let me draw out a few details about this circular process that are really vital. First is development of any predictive asset, no matter whether it's a convolutional deep learning neural network or something as simple as a linear regression model. At their core, all of these models are based on the development or the maturation of models based on effectively analysis of variance. And not a lot of people think about the classical statistics roots of these machine learning models, but analysis of variance tells us when I sell the red ball versus the blue ball, is the demand for those two units the same or different? And there are fixed and random effects. Fixed could be the color of the ball, and random effects could be what sort of person is buying those balls. We can control the color of the ball. We can't control the person buying the ball. In econometrics, we would use terms like endogenous and exogenous, but we're talking about basically the same thing. There are factors in our control and there are factors not in our control, and understanding the difference between those is critical to knowing how we're to build a proper model. Similarly, we need to understand the difference between correlation and causation. Now, most of the people on this webinar are very familiar with this, but it is easy and tempting to reach a decision as a modeler that when we sell the red ball, we cause a certain profit outcome of that sales activity, when it may only be something, you know, that we didn't cause, but it's rather, it's out of our control. The outcome was correlated with the decision that we made. So understanding those properties not only affect how we build a good model, but how we measure the difference in the performance of the model as a function of fixed and random effects, as a function of correlation and causation. Next, to deployment, I'm going to simply say a model built in the lab doesn't perform as well as when it's out in the field. Or rather, a model built in the lab performs better than a model out in the field, because the factors that are out in the field are often unmeasurable by us when we're building it in the lab. And you need to get ready for that. That's just a simple reality. The model is not going to perform the way that you think it did when you were developing it on the computer. Third, decision-making. I like to think of decision-making in the context of predictive analytics as we commit a resource to a customer, an asset, or a source of risk. And what that means is a resource could be a dollar, it could be time, it could be a person's attention, it could be a message delivered over a channel, but it's a resource. We can decide to commit the resource to one option or another option, or not at all, but we have a finite amount of resources. So therefore there are trade-offs that we face in allocating assets to a customer, an asset, or a source of risk. So we use the analytics to guide which resources we allocate and to whom. And when we make that decision making, we're either using analytics as a guide or we're not. If we are using analytics, all the information that could be provided to a decision maker comes down to that decision. Do I go left? Do I go right? Do I sell the red ball or the blue ball? And we effectively collapse all the probabilities at that point. And then we want to know, did we make the right decision? Did the model that we have to assist us in making that decision, did it assist us in making a better decision than if we had no model at all? And so we can measure our decision making, the effectiveness of our decision making in both tactical ways and strategic ways. The tactical way is, for example, we want to know, did we make the right decision? Was it a smart use of analytics and information? Or was it a poor decision? And how would we know the difference between those two? Strategic measurement is usually after several cycles of this develop, deploy, make decisions, measure, and validate. Then we look back and decide, is our effort invested in analytics going in the right direction or not? And do we need to fundamentally consider changing that strategy? I also observe that the frequency of measurement in the field is often not as frequent as it could be. And I think that, you know, the more frequently we can make measurements is more beneficial than taking those measurements infrequently. Finally, there's a value of information. You know, should we go left or should we go right? Should we act now or should we wait? Should we sell the red ball or the blue ball? And every time we take a measurement, it costs us time and potentially costs us money. Even thinking about the act of making a decision to commit a resource to a customer, an asset, or a source of risk is a decision to allocate in one direction or the other. And information is, it costs us money up front to acquire it and use it. But if the decision we make is fundamentally more effective because of the role of the analytics, then there is a superior return on the value of making that investment. in the information, or what I call on the screen, ROVI, the return on the value of information. Information is an asset, just like a physical factory or a method of distributing our products out to customers. It's a valuable asset, and often has more value. The multiplier on the value of information is often stronger than the multiplier of those physical assets. Finally, validation. It's entirely about a couple of terms that I placed on the screen here. And the first is explicability, or something that is explicable is explainable. I don't know why we use explicability in the field of predictive analytics, but that is the term that has got a little bit more traction. So if a model is explainable, I think then the next step you could reach is it's believable. Part of making something understandable and explainable is that it has to be transparent. And there's a real challenge, like the quote from the person from Wells Fargo said, that regulators who oversee bank decision-making want to understand, how does the model work? And how do you make a decision to allocate a resource based on this model? If you understand what the model is telling you, then it is more, and if anybody else could look at that model, a non-involved person, somebody outside the organization can look at that model and understand it, then it is transparent. It also has to be shared. For those of you familiar with sort of the scientific process, one of the last steps in the scientific process after hypothesis generation and testing and measurement and developing findings and recommendations is exposure. It's sharing. We need to publish these results in a format that not just the quantitative experts can look at, but anybody can look at, so that it can be shared and a broader audience can be involved in this process. Finally, we have to be able to characterize the stability of the process generating the data. Now that concept, the process generating the data, it's right out of classic statistics 101. Every piece of information, every datum gets generated by a process. We need to understand that process, because if we don't understand it, if the data is as much a black box to us as the model is, then we will not be able to characterize, is the process stable? If we can't characterize the stability of the process, then we really don't know what we're working with. And our ability to explain, to be believable, to be transparent, all falls away. So this conceptual review of the underpinnings of measurement and validation, which are risk and decision-making, are vital to understand why we would put so much effort into the things we're going to talk about next. And we're going to start by focusing on model measurement. And the first, there's a couple of concepts that we're going to cover. The first is stability, followed by performance, followed by calibration, and finally prediction. And I'm going to use these terms in a way that they're used in the financial services industry. However, there's broad applicability of all the different ways we're talking about these concepts. So whether you use these terms going forward or not, I'll explain what each of them means. So stability is how stable are the things we're measuring, and how stable are the relationships among the multiple things that get involved in measurement and validation. And there's really two fundamental types of stability. The first is system stability. And system stability focuses on the thing we're trying to predict. We might, in the machine learning field, we might call that a target. In the statistics field, we might call that a dependent variable. System stability can be captured by a couple of different indices, and one of the most common ones is called the System Stability Index, or the SSI. Now this table, the way that we measure system stability is to stack rank all of our, say, customers by score bins. Typically, we do this with quantiles, like 10 quantiles are called deciles, or 20 quantiles are called vigiciles, 100 quantiles are called percentiles. So we used, in this example, there are typically in financial services, we'll start by using deciles, and we characterize a model by its score points. So the first pool, and there's actually a first pool not appearing in the table because it's all those customers who have a missing score. So that's why you don't see a pool 01, but pool 02 are those customers with scores between 0 and 20 points. Pool 3 is between 21 and 47 points, and so on. And the most important thing you're going to see here is development accounts. That's the breakdown or the spread of customers we had in our development sample when we built the model. And at any point in time in the field, we can look at the number of actual accounts. And there's always going to be a difference because the amount of the spread of accounts in our sample is going to definitely vary from the spread in the population. The bigger that spread varies, the greater the SSI in total. So you can see that the aggregate stability index it will be calculated as the sum of these numbers. The bigger that the number gets, the less stable the system is. And we can also show this graphically. So the chart on the left is a chart of the marginal SSI by risk pool or by decile. Now the lowest pool, and this is a really important concept, the pools with the smallest numbers in these examples I'm using, we're characterizing risk. And the higher the number of score points, say this last pool, 210 to 238 score points, that characterizes customers that have relatively low risk of an adverse event like defaulting on a loan or being a fraudulent actor or being a financial criminal. Those are the kinds of adverse events we're trying to characterize and then avoid. The lowest score points, those are our highest risk entities, and those are the ones we most want to use our models to find. Now, if this was a marketing problem, the customers, say on the left-hand side of the distribution, would be those who buy our product versus those who don't buy our product. Typically, fewer people will buy our product than those who don't choose to buy our product. The mathematics is the same, but it's the left-hand side of this distribution over here that we really want our model to get right. So you can see the blue line are the development accounts and the red line is our actual accounts in the field. And fortunately, on the left-hand side, our process is relatively stable. We have roughly the same amount of spread on the left as where our risk is greatest in the development versus the actual pool. The left-hand chart is a marginal breakdown by pool, and the right-hand side chart is simply the same numbers, but cumulated from left to right. There's another kind of stability. So the first stability measure we're talking about was system stability. The second one is called characteristic stability. Some people call this attribute stability, but it's the same concept either way. Now there's a lot in these, in this series of small multiples. I'm going to explain what you're looking at here. The left-hand pair of charts, these are the frequency. These are looking at frequency of customers. And on the right-hand side, we're looking at incidence rate of the default adverse event. So frequency counts on the left, probability of an adverse event on the right. The rows, so 0 through 9, now these are not risk pools. These are actually periods of time. So 0 is when we built our model. And as time elapses and we take measurements, we took a measurement in period 1, in period 2, in period 3 through period 9, you're seeing the effect of the migration of behavior over time. Finally, each chart, say for example, this chart right here in the northwest corner, this is the frequency count across 6 buckets or up to 6 buckets of this variable here, this particular data field, GRP CL age, this is the age of a line of credit. So short age means you've had a loan for a relatively short period of time, and longer age means you've held that loan for a longer period of time. And the next variable is called debt to income ratio. This is often used in banking as a measure of if you carry a lot of debt Say you have $90 of debt and you have $100 of income, that's a 90% debt to income ratio. Typically, banks want to loan money to customers who are managing their credit wisely, and typically those customers have lower debt to income ratios. Now, if you look at the change in this column, you'll see we have a fairly broad spread of credit line ages when we started building the model, and as time elapses, the frequency counts are getting much older. Now, this is not uncommon. This happens when you're looking at a single vintage of customers measured at a point in time, and you don't, and so all the customers who were granted a loan in, say, January of 1990, and then each of these measurement periods is a year. Well, over time, you're not adding new customers into that vintage, and those credit lines get older, and so we'd see this drift to the right. Now, if we look at the corresponding chart on the right, which is tracking, we know the credit line ages are getting older. Do we see a change in the distribution of risk? The higher that the y-axis is, the higher the default rate is measured to be. And you can see in time zero, we typically have most customers, there's a spread of customers that looks like this, and it looks pretty much like that, with the lower risk on the left and the higher risk on the right. We're seeing the spread of credit line ages with respect to risk being relatively the same, even though they're getting older. So what we could conclude from that is, even though credit line ages get older, the spread of risk across those quantiles of credit line age are not changing. However, let's look now at debt to income ratio. The spread of debt to income ratio doesn't change a lot over time, but the risk changes quite significantly, where the highest debt to income ratio customers have the highest risk, as we just explained. But over time, this risk gets broader. The amount of risk starts to become more broadly spread. Sort of, you could almost think of it as water in a bathtub. It's getting spread to the left. Not dramatically, but it is moving to the left. And so we can see that the event stability, or the characteristic stability with respect to debt to income, is moving over time. Now, we're looking at a variety of dimensions all at once using these small multiple bar charts. And this is the sort of analysis you'd want to do for every independent variable that you're looking at in your model, to understand, as debt to income changes, how does risk change over time? All right, now let's move forward and talk about performance. Performance is the ability of our model to divide customers into high risk and low risk categories. In the chart to the left, we're looking at a metric called gain. So as our customers on the left-hand side have the highest risk, and our customers on the right have lower risk. What we want to look for is, if we had no model at all and we randomly assorted customers, we would see this straight diagonal line up and to the right. This means the random model. And the blue line is the perfect model. If our model had all true positives and all true negatives, this is the best our model could do. And what our model is currently doing is sort of in the middle. We also have this measure of KS, or the Kolmogorov-Smirnov score. Now, the KS statistic is a measure of how much does our model group our adverse events, or our bads, into one bucket, and our not adverse events, or our goods, into another bucket. And the KS is measured as you accumulate the bad rate from left to right, from the most risky to the least risky customers. What we want to see is there should be some distance between the cumulative bads line and the cumulative goods line, because we want our riskiest customers to have the lowest scores, and the KS is calculated as the vertical distance at the greatest spread between the cumulative bad rate and the cumulative good rate. This is a measure of watching where does our model do the best job of discriminating between bads and goods. Now, each of these charts is a static look at one period in time, but we can also look at this over time, just like we did in the previous chart, where the black line is watching the accuracy ratio, or the Gini statistic, which is, there's a pretty straightforward transformation of the measure of model gain into the Gini statistic. We can see that it started up here, but it's starting to degrade over time. And the same thing is happening on the KS statistic over time. So it's vital to watch both of these statistics as you continue to measure the data over time. The third character, or the third family of model measurement statistics, is called calibration. So we started with stability. How stable is the process? How stable is the spread? And how stable are the relationships between the things we're measuring? The next one was performance, or the ability of a model to discriminate between bads and goods. The third measure, calibration, is a measure of precision. How accurately is our model actually predicting the rate of, say, default rates? And so these charts are looking at the blue line is the estimate of the probability of default as our scores go up, so estimate versus actual. And the red line is the actual rate of default. And we're seeing that while these charts, or while these lines go up together, they're not perfectly calibrated. And so the tighter that these two lines could get, the better job our model is doing in terms of producing a well-calibrated estimate of risk. That's important because, especially when we go to the next category, which is prediction. So we've been talking about default rates, and now we're going to switch from a classification model, a binary outcome, to a continuous outcome. And so that we might use loss given default. So in this statistic, or in this chart, in this chart here, 1 to 10, these are our risk pools, from most risky to least risky. And the line on the top is our actual risk in each pool. And you can see that in the most risky pool, our loss given default, the number of dollars we would lose if a customer defaults, is higher. And over here in the 10th pool, the least risky, it's further to the left. We see the actual versus estimated chart. And what we want to see is that these two distributions should basically sit right on top of each other. This is at period 0 when we develop the model. This is at period 6. And while it's hard to tell, you can kind of see that, first of all, there's more horizontal spread in a number of these charts on the bottom. We can also look at the residual, the delta, or the difference between these two. The black line over the risk pools, this is our riskiest pool, and the black line is the actual loss given default, and the dashed line is the predicted loss given default. So basically you can see what this difference is as this distribution moves and this distribution moves, we're getting a less accurate estimation over time, where we're seeing the actual and the estimate move further apart over time. This is a problem for this model because while our model is well calibrated in the lower risk pools, this most risky pool, our model is not that well calibrated. So we would want to spend more time tightening up how this model is performing in terms of this expected risk model. Now let's move to model validation. When Corios helps a client validate their model, we use everything we just walked through in terms of model measurement and a lot more. And so you're seeing on the screen a hierarchy we use. There's a set of process due diligence questions we pursue. There's a set of documentation due diligence questions we pursue. And there's a data quality and integrity set of questions we pursue, in addition to the model measurement questions I was just sharing with you. There's a whole lot on this screen that represents the work that a model validator pursues in order to understand how well this model is built. It's not simply a matter of how accurate it is in the lab. There is a lot of sources of information that need to be pursued in order to understand how well validated this measure is, or this model is. This might seem pretty overwhelming, and it is. It also might seem a little scary. It is scary to have somebody else look at your work. You know, none of us want to, all of us have that fear of being found out. The more work you put into understanding how a model validator will look at your work, the more well-prepared you can be. Even though it's tedious and a little scary, I want to encourage those of you who find the process of model validation to be valuable to really pursue it, because there are not nearly enough people available in the market to perform model validation compared to the potential workload that exists out in the industry, particularly in the financial services industry. So to set yourself up for success in terms of supporting the model validation activity, I have a couple of recommendations. So how to measure and validate your own models. And the first recommendation I have is flip the script. So many times, the process that I showed you when we first looked at this particular visual, the arrows started at development and went up and around to the right. I want to encourage you to think about predictive analytics and machine learning in the reverse order. Start with validation. What do I need to make my model validatable? I need to have it documented. I need to have it transparent. I need to have frequent levels of measurement. I need to have a breadth of measurement metrics that I'm capturing. And I need to make sure that my model is explainable and believable. Then as I measure, I want to take a measurement as frequently as I can, focused not only on the model's metrics itself, but also on how are people making decisions using my model, and what is the impact of those decisions on the business the business decisions that they're making around allocating resources to customers, assets, and sources of risk. Then with that framework in mind, you can start to think about, how do I deploy my model so that I can put measurement into the process? I can put validation into the process that gets deployed. And then I come all the way back to model development to make sure that the way I develop my model, the way I train my model, was built, educated by doing it entirely in reverse. Instead of the way I see this actually being done is, people are so focused on estimating a model and running a really cool convolutional neural net that they forget they're going to have to do all these steps later. And so flip the script, do it in the reverse order first, and then you will have set yourself up really well when the time comes to validate it. The second thing I would encourage you to do is to become more well educated on the full set of processes involved in what I like to call this field of model measurement and validation. I like to call it predictive analytics asset management, because really this model, or all of our models, they are assets, and we want to manage those assets carefully. I wrote a book and published it in 2017 called Skate Where the Puck's Headed. And it's a book based on my roughly 30 years of being in this field. And you can buy it at a very reasonable rate from Amazon for $4.95 to download the digital book, the ebook, by going to this website, skate.coriosgroup.com, and there you can get the link to buying it on Amazon. It's a very reasonable price for the book. And because I'm really just interested in sharing this, this long career that I've had in doing this. And the whole 7th chapter takes what we've talked about in 45 minutes and breaks that out over roughly 30 to 50 pages. The final resource that I'd like to make available to you, and this is exclusive to the Ideas audience, is this, all the metrics that I reviewed with you around model measurement. I actually have built about a 30-page, fully detailed example of what we do for our customers in the real world when we measure these metrics. And all of the many of the calculations of how they are calculated from the raw data are documented in this report. Now, not every single line of code, but the fundamental mathematical principles of these metrics used for stability, performance, calibration, and prediction. So if you go to this URL, go.coriosgroup.com/measure-validate, and we'll leave this on the screen for a few minutes while we take questions. There's no charge for this. You can download this roughly 35-page PDF report that goes into a lot of detail around all these measures and provides you with examples you can replicate. So I think I will, so that's the end of my prepared remarks. So let me take the questions. So it looks like, here we go. There weren't any questions. So if you have any questions using the app, this would be a good time to ask them.
I think, we got one question, not from the Q&A window, from the chat window.
Ah, okay.
Let me see. What's the URL to download? I think, she's asking the download, link.
Yeah, actually, so the report, the URL is right up here at the top of the screen. So just put https:// in front of this link, go.coriosgroup.com/measure-validate. That's the URL for the report. And then the book is skate.coriosgroup.com. So https://skate.coriosgroup.com. And that's where you can download the book. Or that'll get you to the Amazon page where you can order the book for your Kindle or your other ebook reader.
Okay, so we got another question from Christine. I think the question is certification in machine learning. I think, the question is, what do we think is a good certification for machine learning? Yeah,
that's a great question. Well, our field is very broad and it moves really, really fast. Back in the day, back in the 80s and 90s when I was a student, the best way to get certification was to get a degree, a bachelor's degree or a master's degree in this field. That's not really the way that you're required to do it anymore. However, there are many different places to go where you could get this understanding. I have found, in terms of understanding the technology infrastructure that supports machine learning, Cloud Academy is the resource we use to better understand how you could use, say, Google Cloud, AWS, and Azure as a technology platform for modeling, for building models and deploying models. And I have found some pretty good courses on Coursera and Udemy around, like, for example, how to build models using Spark or how to build models using Python. My friend Randy Betancourt has written a book that's called Python for SaaS users. So SaaS isn't necessarily the most dominant provider of software for machine learning like it used to be, but SaaS has some pretty good courses that you can take. But my friend Randy has published a book called Python for SaaS users that takes what anybody who grew up like I did 30 years ago, and we all used SAS to do this, and it teaches you how to do the very same sorts of things using Python. So that book's not available on the market yet, but it's coming out, I believe, next month. So if you go to Amazon and you look for Python for SaaS users by Randy Betancourt, Betancourt, you can pre-order the book today.
Okay, so I think there are two more questions. Robin, can you, because we only have 7 minutes there, so can you pick up, we have 2 more questions in the Q&A window.
Yeah,
and,
sure.
3 more questions in the chat window. So can you open these 2 windows to pick up, whatever you think, important. We can, because we have to take priority,
sure.
We only have 7 minutes.
That makes sense, Jason.
Pick up whatever.
So Alice asks a question, how do you know that you have validated enough that your model is mature? That's a great question. So virtually every large bank in the country has actually departments of people who are called model validators. There's also typically executive oversight committees that are called like the Model Validation Oversight Group, or something like, words to that effect. So they typically break models into something like 3 categories. And it has to do with the amount of risk and the amount of materiality that the model represents. So if a model is being used for, say, marketing and sales activity, it's usually in the lowest tier of sort of stringency. If it is a lending model, that is definitely a much more high-rated model. Particularly, there's different kinds of lending strategies that banks use, and if it is a pre-approved lending model, then it's a high priority model, as are anti-money laundering models or financial crime or anti-fraud models typically are the highest stringency. Typically the reports for a low stringency model might be 20 to 30 pages long. The report for a high stringency review could be 60 to 100 pages long. That's just a measure of the number of pages of the report, but being able to categorize them is one of the first ways to think about that. Srishti asks, how is model validation different from model verification? And I don't know, because I don't know what you mean by verification. So I don't, but typically in the financial services world, we call this model validation. I think it's possible that that no matter what terminology you might use, the principles of how you would understand, if you go back to, you'll see in the recording of this slide, and we can actually see it right here, this hierarchy, so model purpose, model data sources, model output, model governance, and so on. These categories of things are the sorts of things that would, I think, be endemic to any process of independent review of a model as an asset and as a decision-making resource. Jason, there's a question here. Where can I find a recording of the webinar? And I think I'll leave that to you to answer.
Yeah, so for IDEAS, International Data Engineering and Science Association, we have a channel on YouTube. So you go to YouTube, search International Data Engineering and Science Association, you will find hundreds, YouTube, recording, about the conference talk, the online webinar talk. You can find a lot of, videos there, including, today's. We will post that early next week.
Cool, that's great. There's a chat window question from Manoj who asks, please let me know who can mandate that validation happens, that documentations are proper, that entry and exit criteria for the methodology I mentioned. So there are stipulations. So in the United States, there's an organization called the Bank of International Settlements. It's essentially an oversight group that provides guidance to all banks of a certain size, and that size has continued to grow over time. That stipulates the practices that banks should follow to perform model validation. One of the current standards is called SR 11-7. And if you download that report, if you just Google SR 11-7, you can read more about the guidance that financial institutions are expected to follow. Every year or every couple of years, those standards get more demanding, more specific, and more prescriptive. So this is a moving target. Now that's the external market forces. Inside every financial institution, there is typically an audit function called model validation group, who are the people who decide which models need to be validated, even the definition of what is a model. In the banking industry, a model is any business rule, whether there's a statistical function or just an Excel spreadsheet that says this group of customers gets this product or this treatment, and this group of customers over here does not. That's a model in many ways, even though there's no machine learning concept to it. So Jason, I think we're just about at the end of our time, so I'll turn it back to you.
Okay. Yeah, thank you, Robbie. And I think, yeah, definitely we have only 1 minute. Please, do us a favor. We have a poll on the screen. So especially the third question, what other topics or contents you want, you would like to see from us? Okay, that is a good place. You can vote what topics we will provide in the future webinar. And thank you again, Robin, and thank you all the attendees, and have a good weekend.
Thank you so much, everybody. Thank you, Jason.
Thank you. Bye.
Good night. Bye-bye.